A acidic or diprotic acid has two hydrogens it can donate. A dibasic base is capable of accepting two protons or two hydrogens. And so let's take a look at what we do with the dibasic base. What we're going to do is look for all the hydroxide contributors to this. And so when I look at a dibasic base like this, a base will hydrolyze water to form, in this case, bicarbonate and hydroxide. And so this is what we call Kb for carbonate. Even though it's capable of accepting two hydrogens, we only accept one hydrogen at a time. Kb for carbonate is also called Kb1 for carbonate. And so it's the first proton acceptor for this system. Okay, but bicarbonate itself is also a base. So bicarbonate can in turn accept another proton to form carbonic acid and hydroxide here. And so this is what we call Kb for bicarbonate, which is equal to Kb2 for carbonate. And so carbonate is capable of accepting two hydrogens, Kb1 and Kb2. And it turns out we also have to worry about water, that is Kw. And so if I look at Kw, it'll be H2O liquid plus H2O liquid. We're going to have auto ionization to form hydroxide. And so there are three hydroxide contributors to this system. And so for bases, we look for all the hydroxide contributors. For acids, we look for all hydronium contributors. And so for example, HCl, we looked for HCl and water. And the total hydronium was the sum. Well, the total hydroxide is going to be the sum from all the contributors. Can you think of any other hydroxide contributors? No, there isn't. But there is one issue, though, and that one issue is with bicarbonate here. Bicarbonate's amphoteric. Amphoteric means bicarbonate can act as an acid, and so it has a Ka, or it could act as a base, and it has a Kb. So if we look at the Ka equation for bicarbonate, bicarbonate can also donate a proton to water as an acid. If it donates a proton to water, then we're going to form hydronium and carbonate. So there are two things that we do with this. One, for base solutions, such as carbonate, only hydroxide contributors are considered. And so this Ka is a hydronium contributor, not a hydroxide contributor, so we ignore it. I'll write ignore in parentheses, not parentheses, in quotation marks, because we don't really ignore it. Ignore H3O plus. if solution is, for example, amphoteric, sodium bicarbonate, then must consider both Ka and Kb. Ka and Kb and one other one, and that's Kw. So Ka and Kb and Kw simultaneously. Since we have a carbonate solution, that's considered a base solution. If we had a sodium bicarbonate solution, that would be considered an amphoteric solution, and then it gets a lot harder, because whenever we have to do simultaneous equilibria, the math gets difficult. Did I show you the simultaneous equilibria example yet? No? Okay. Let me show you a simultaneous equilibria example right now. There are two main methods that we use to solve multiple equilibria. One is stepwise, the other is simultaneous. And let's consider something like this. I'm going to consider 1 times 10 to the minus 8 molar HCN. The first thing you notice is the concentration of the acid is very, very small. If the concentration of the acid is very small, then water could be a significant contributor to this. Let's take a look at the Ka for this next. Let me pause this for just a moment. So that's hydrocyanic acid. Take a look. Hydrocyanic acid is 6.2 times 10 to the minus 10, the Ka value. And so HCN is going to hydrolyze water, and this is going to produce hydronium and cyanide. Okay, and we know that Ka for this is 6.2 times 10 to the minus 10, which is going to equal the hydronium concentration at equilibrium times the cyanide concentration divided by the HCN concentration at equilibrium. And then we can go ahead and solve this. Initially, I'm going to have 1 times 10 to the minus 8 molar. Water is a pure liquid. Hydronium, I'm going to assume nothing's hydrolyzed yet. And so the change is we're going to lose a little bit of our HCN. It's not a strong acid, so we don't lose all of it. It's a weak acid, so we're just going to partially ionize or partially hydrolyze it. And so that's going to be minus X plus X molar plus X molar. So that at equilibrium, we're going to have 1 times 10 to the minus 8 minus X molar, and then X molar, and then X molar here. And then we need to solve for X. So it's going to be X times X, which gives us X squared on the top. And then on the bottom, we're going to have 1 times 10 to the minus 8 minus X. And this has to equal 6.2 times 10 to the minus 10. Then automatically, I always use a simplifying assumption, because Makes the math a lot easier if it works. If it doesn't, then we'll have to use the quadratic. But 1 times 10 to the minus 8 minus x should simplify into 1 times 10 to the minus 8. Okay, and then solve for x. X is going to equal 6.2 times 10 to the minus 10. Times 1 times 10 to the minus 8, and then take the square root of that answer. And I get 2.48 times 10 to the minus 9. I want to make that 10 to the minus, I'll just leave it there. And let's take a look at the percent change. Percent change is going to be the change, 2.48 times 10 to the minus 9 divided by the initial, which is 1 times 10 to the minus 8 times 100%. So this is going to be 10 to the minus 1 times 10 squared would be 10 to the first. So this is going to be 24.8%. That's greater than 5%, and so the essay is not valid. So the essay is not valid, so we'll have to use the quadratic then. So I'm going to get this into quadratic form. I'll do it over here, use quadratic. Which means we're going to get x squared plus 6.2 times 10 to the minus 10x minus 6.2 times 10 to the minus 18 is equal to 0. Let's see, 10 to the minus 10, 10 to the minus 8, 10 to the minus 18, yeah. Alright, then we're going to go to the quadratic solver and solve it. 10 and 18. So here I'll do 6.2 times 10 to the minus 10. Over here I'll do negative 6.2 times 10 to the negative 18. 2.1992 times 10 to the minus 9. All right, let's go ahead and plug that in. So I'm going to make this 10 to the minus 8. So if I make this smaller, I make the coefficient, or if I make this bigger, 10 to the minus 8 is bigger, I make this smaller. So this is going to be 1 times 10 to the minus 8 minus 0.21992 times 10 to the minus 8. Let's see what that comes out to. So we lost about 21%, and we have about 78%. We lost about 22%. And so we had 22% ionization or 22% hydrolysis. That was the percent change over here. It's the change over the initial. So this is 22% ionization or hydrolysis. It seems a little high. I better double check my calculation. It seems a little bit high because this acid's fairly weak. This acid is 10 to the minus 10. And I'm getting 22% hydrolysis, which seems a bit high for how weak the acid appears to be. So let me double check my quadratic here. X squared plus 6.2 times 10 to the minus 10x minus 6.2 times 10 to the minus 18. And check the quadratic. 6.2 times 10 to the minus 10 minus 6.2 times 10 to the minus 18. 2.1992 times 10 to the minus 9. And so 1 times 10 to the minus 8 minus 2.1992 times 10 to the minus 9. I guess that's right. All right, this is going to be molar. And then over here, this is just x, so it's just going to be 2.1992 times 10 to the minus 9 molar. And this one will be the same, 2.1992 times 10 to the minus 9 molar. All right, so what we're going to do is we're going to double check our K value to make sure it comes out close to what was given. So take the hydronium times the cyanide, which is the same, so I'll just square that, divided by the HCN, which came out to 0.78008 times 10 to the minus 8. And see what we get. I get a K value that's equal to 6.199 times 10 to the minus 10. And the K value, the given K value is 6.2. So we're good here. Values check out. But the problem is this isn't the only hydronium. If this was the only hydronium producer in solution, I'd stop here. Then I could get the pH. But there's another hydronium ion producer present. What is it? It's water, Kw. So we're going to call this step 1, because what we do is we try to just do it stepwise. The stepwise calculation is much easier. And so we're going to do this one exactly the same way that we did HCl. We'll do step 2. And so step 2 is going to be H2O liquid plus H2O liquid. And then we're going to figure out how much additional hydronium we're going to get from auto ionization of water, hydroxide. And so the initial, this is pure water, pure water. Oh, look at those. The initial hydronium, here, we don't start off with 0. We don't start off with 0 because we have some hydronium from step 1. And so we're going to take this hydronium that we generated in step 1 and then drop it down to step 2. And so that means that 2.1992 times 10 to the minus 9 molar is going to come from step 1. And here we assume that no hydrolysis has occurred, so there's no hydroxide. So all that hydronium came from the previous step. Okay, now why don't you finish this here? and figure Kw. So figure out how much additional hydronium we get from the water autoionization. Okay, did you get it? Did anybody get X? No? Okay, we'll just get it then. This is going to equal the hydronium concentration times the hydroxide ion concentration, which is going to be 2.1992 times 10 to the minus 9 plus X. Times X. All right, Kw is quite small. It's 1.0 times 10 to the minus 14. And so we expect the change to be small, but I worry about the simplifying assumption here because the initial amount of hydronium is so small. But I'm not going to worry about it too much. I'm just going to try the assay and see if it works. If it fails, that's fine. I'll just use the quadratic. So applying the SA, then this is going to simplify to 2.1992 times 10 to the minus 9 times X. And therefore, X is equal to 1 times 10 to the minus 14 divided by 2.1992 times 10 to the minus 9. And that gives an X of 4.547. 4.547 times 10 to the minus 6. Here. All right, when we look at it, the change is bigger than the initial. So there's no way this is going to work. In fact, if we calculate the percent change, that's going to be the change divided by the initial, which was 2.1992 times 10 to the minus 9 times 100. And this gives us a 206,000%, which is way more than our limit. And so SA failed. And therefore, we have to use a quadratic. Right? And so getting this into quadratic form, I'm going to get x squared. And that's going to have to be a let me make sure this is still recording. Yeah. Plus 2.1992 times 10 to the minus 9x minus 1.0 times 10 to the minus 14 is equal to 0. All right, so we're going to plug that into the quadratic here. To 1992 times 10 to the minus 6 and then minus 1 times 10 to the negative 14 gives us 5377 times 10 to the minus 9. All right, when we did the simplifying assumption, we got 4.547 times 10 to the minus 6, so quite a big difference here. But let's check this. And so I'm going to get 2.1992 times 10 to the minus 9 plus 4.5337 times 10 to the minus 9. Maybe I'll just go 4 decimal places here. And so this is going to give me
It was 4.5377, right?
oh yeah, 5377, that's right. .7369 times 10 to the minus 9 molar. So this is the amount that came from the HCN. This is the amount that comes from H2O. So which one contributed more hydronium according to this calculation? The water. But let me double check in case I made a mistake with the calculation. So I'm going to get 4.5377 times 10 to the minus 9 molar hydroxide. And so we need to compare, or at least multiply these two concentrations to see what they comes out to. So 6.7369 times 10 to the minus 9 times 4.5377 times 10 to the minus 9 equals, oh, I made a mistake. Because when I calculate K comes out to 3.057 times 10 to the negative 17. That's way off. Because the K is supposed to equal 1.0 times 10 to the negative 14. I'm getting this. This is way off. And so it's not just a rounding error, there's some kind of calc error. And so I need to double check the calculations here. So I have 2.1992 times 10 to the minus 9. It came from the previous step here. Plus x times x. So I get x squared plus 2.1992 times 10 to the minus 9x. And then subtract this term. Minus 1 times 10 to the minus 14. It should equal 0. And then I plug that into the quadratic. Let's see. 2.1992 times 10 to the minus 6 x. I see my mistake. See, I put in 10 to the minus 6. It's 10 to the minus 9. So let me redo that here. It should be 10 to the minus 9. And this is correct. 1 times 10 to the minus 14 negative. And that gives me 989.06 times 10 to the minus 8. Let's redo that. It's way off. That's because this x was way off. All right. So I redid the quadratic there, And we get this value for x. So x is equal to 989.06 times 10 to the minus 9. Oh, not 9, 8 times 10 to the minus 8. All right, so let's redo the hydronium ion concentration over here. This is going to be 2.1992 times 10 to the minus 9. So what I'm going to do is I'm going to make this smaller, 10 to the minus 9 smaller than 10 to the minus 8. That means I got to make this bigger. So this is going to come out to 98.906 times 10 to the minus 9. So let's go ahead and add those two up. So 2.1992 times 10 to the minus 9 plus 9.8906 times 10 to the minus 8. And I get 100 point, or not, 101, sorry. .105 times 10 to the minus 9. So when we look at it, this came from the HCN. This came from the H2O. So how much of the hydronium came from the H2O? About 98% of the hydronium. And so step 2 was the major contributor of hydronium here. It wasn't the HCN that contributed to the most, it was the H2O. But we have a problem here. And the problem is this. If the hydronium grows by 98%, let's say, what's that going to do to the previous equilibrium? The previous equilibrium I had double checked. And it was pretty much right on, 6.2 times 10 to the minus 10. But now, what happened to the hydronium? The hydronium is no longer 2 times 10 to the minus 9. It's more like 101 times 10 to the minus 9. So if I plug in 101 times 10 to the minus 9 up here in the numerator, is this still at equilibrium? No. What happened was Le Chatelier's principle. We had a system at equilibrium, step 1, and now we're perturbing it by adding or dumping in another 98 times 10 to the minus 9 molar hydronium, which is a huge addition. What does Le Chatelier's principle say? It's going to shift the equilibrium. And so what happens here is this was a significant addition of hydronium. This will perturb step 1. So if we go back to step 1 and then plug this in for the hydronium and then do a Le Chatelier's type calculation, we can fix it. But once we fix it, then it's going to shift again and it's going to perturb step 2. So we get into a circular loop. And this circular loop is we fix the left side, the right side goes out of whack. We fix the right side, the left side goes out of whack. So we'll never be able to never be able to fix this. It'll be endless. Therefore, what we need to do is solve this simultaneously. In simultaneous, we do both ice tables simultaneously. And so here I'm going to put down the HCN ice table. And then the H2O ice table. And I have to solve these simultaneously. How do you do that? Well, this is how we're going to do it. Initially, we're starting off with 1 times 10 to the minus 8 molar HCN. Water is a pure liquid. And we're going to assume that nothing's hydrolyzed yet. And so we have 0 molar cyanide. But we're going to have some hydronium from water. The hydronium from water I'm going to call Y molar. This is the hydronium from water. KW. Okay, now I'm going to let this equilibrate. So we're going to lose some HCN. We're going to gain some more hydronium. And we're going to gain some chloride. And so we'll just do minus X plus X plus X. So at equilibrium, I'm going to have 1 times 10 to the minus 8 minus X molar. And then over here, for hydronium, I'm going to have the combined Y from KW and X from Ka. So this is going to be Y plus X molar. And then cyanide will be X molar. At the same time, I'm solving this other ice table. And so water is pure liquid, so we'll omit those. And then we'll have hydronium. We're going to assume that no water is hydrolyzed, so the hydroxide is going to be 0. But there is going to be some hydronium. The hydronium is going to come from HCN. How much hydronium are we going to have from HCN? We're going to have X molar from HCN. So this is from Ka. Hydronium from Ka of HCN. And then we'll let this equilibrate. So this is going to be plus Y molar plus Y molar. So at equilibrium, I'm going to have X plus Y molar and then Y molar here. So now we have 2 unknowns, X and Y. And we can generate 2 equations, so try to solve this for X and Y. So how much time do you think you'll need to solve this? Algebra. 2 unknowns, 2 equations. What do you think would be a reasonable amount of time to solve it? Depends. You know, it depends on how good you are with algebra. Is algebra pretty easy or pretty tough? Somewhere in between. All right, try to solve it. See what you can come up with. One of the methods for solving X and Y is using these K expressions in the ice table. Or another method is by using what we call mass and charge balance equations. Turns out that most people can't do this. It's too hard. A few people can do it, but the algebra is pretty tough. It's not so easy. So what we're going to do for Chem 1B is you should just be able to set it up. If you can set it up where we have two equations and two unknowns, that's enough. But the actual solving for it is not going to be required. It's going to be beyond the scope. As maybe a couple of people will do it for bonus. But it's not easy for sure. It's a hard calculation. I'll post something that shows how to do it. But the reason we have to do it simultaneously is because of this perturbation. So whenever we have simultaneous equilibria, it's going to be tough. We try to avoid that by doing stepwise equilibria, which is much easier. And so we just end up here. That's about it. Rest is difficult.
So with the stepwise, do we just stop after adding the hydronium?
You'd have to be able to recognize that.
It would change it.
Yeah, you have to recognize if it's stepwise or simultaneous. So for example, if you solve this and you just left it stepwise, then you'd be wrong, basically. You get the wrong answer. So you'd have to know that, oh, I got to stop here. This has to be solved simultaneously. This is how I start it. And maybe that's as far as I'll get.
I think it's only when like water contributes a great amount.
No, it's simultaneous, must solve simultaneous for anything where the current step perturbs the previous step. Whether it's water or step 2 or whatever, if the current step perturbs the previous step, we have to use simultaneous. And so you do it each step at a time. Let's say there are 3 steps. Does the second step perturb the first step? If yes, then stop. We got to solve it simultaneously. If no, then go on to step 3. You know? In fact, we'll do an example here. And so the way you solve this is you have to use some tricks like simplifying assumption and other things. It's making it difficult, but if I put something like this on the test, it would just be setting it up, and then as a bonus, you could actually complete the calculation. Usually like 1 or 2 people are able to complete the calculation per year, just to give you an idea. But I'll hand out a key for this one later. It would just take too long to go through it now. So let's try this. This is from the lab. We had sodium carbonate. And we want to figure out what is the pH for this. Figuring out the KB is a little bit more tricky. So we'll just figure out the pH. The sodium ions aren't going to impact the pH. Those are neutral. However, the carbonate ions, these are what we call a dibasic base. Have I talked about dibasic bases already? Yeah. And so we have multiple contributors to hydroxide. If we have multiple contributors to hydroxide, what we want to do is we want to try this stepwise. We always try it stepwise because simultaneous is too hard. Starting with the largest K and then going down. So the largest K is probably going to be for carbonate. That's going to be the most basic species present. Sodium ions are neutral. Water is not all that basic. So we would predict carbonate. So this is going to be my step 1. And this is going to produce bicarbonate and hydroxide. And we'll need our Kb for carbonate, which is Kb1 for carbonate. Which is not in the table. The Kb value is not in the table for carbonate, and therefore what would you look for?
The Ka for bicarbonate.
Yeah, exactly, because the Kb for carbonate is going to equal Kw divided by the Ka for the conjugate acid. The conjugate acid is going to be bicarbonate. Depending on which table you look at, Ka for bicarbonate is actually Ka2 for carbonic acid. Ka1, we lose the first hydrogen. That would be for carbonic. Ka2 would be for taking bicarbonate and losing the second hydrogen. So either we look for Ka for bicarbonate or Ka2 for carbonic acid. And what we see is we see both. Here's Ka1 for carbonic acid, 4.4 times 10 to the minus 7. Here's Ka2 for carbonic acid, 4.7 times 10 to the minus 11. Ka2 for carbonic acid is the same thing as Ka for bicarbonate, 4.7 times 10 to the minus 11. And so we'll plug that in here. 1.0 times 10 to the minus 14 is Kw divided by Ka for carbonic acid, which is 4. Or was it bicarbonate? Ka1? 4.7 times 10 to the minus 11? Okay. Yeah. 4.7 times 10 to the minus 11. And this gives us what? One times 10 to the negative 14 divided by 4.7 times 10 to the negative 11. This gives me 2.1276 times 10 to the negative 4. This acid is quite a bit stronger than hydrocyanic acid. Or no, this is not an acid. This is a base. Sorry. Shouldn't be comparing acids with bases. All right, that's going to be the largest Kb. This is a lot bigger than Kw. And it's going to be more basic than bicarbonate. Okay, so initially we had 0.1 molar. Water is pure liquid. And then we're going to say this is 0 molar and this is 0 molar. All right, go ahead and fill out the rest of the ice table and solve for X. tell you. So you use the simplifying assumption. So you got x squared over 0.1 minus x. And then you did the SA. And then what did you get for x?
0.004612.
And what did you get for your percent change?
4.6.
So here's what you do. That's at the limit. Is that still acceptable? It's less than 5%. So if you have limited time, you would go with it. But since it's at the limit, the error is going to be larger. And so if you have more time, what you could do is you could try to get it better by using the quadratic. And so let's go ahead and calculate the concentrations. What did you get for the concentration of carbonate after?
0.09538.
And then the bicarbonate is just X, and the hydroxide is just X. 004612. 004612 molar. 0.004612 molar. And that gave you a K value of what?
2.23 times 10 to the minus 4.
So we should get 2.13. It's close, right? It's pretty close. But we probably can get better. And so if there's time available, what you would do is you'd just do the quadratic. And so let's do the quadratic and see how much better it would have come out. So if we use the quadratic, then let me get this into quadratic form. And that's going to be x squared. We're going to add 2.1276 times 10 to the minus 4 x, and 0.1 10 to the minus 1 10 to the minus 5 minus 2.1276 times 10 to the minus 5. This is going to equal 0. And so we're going to plug this into the quadratic. 1276. 1276. Let me fix this one. This should be -4. Okay. And so we get 004507. 45074. Let me try that. So with the simplifying assumption, we get 4612. Without the simplifying assumption, we have 4507. So 4507 is more accurate. And so let's go back and calculate this one here. So this is going to be 0.1 minus 0.004507. So this comes out to 0.9549. 0.09549 versus 9538. A little bit off. And this comes out to 004507. 0.004507. And so checking the K value here, the K value comes out to 2.127 times 10 to the negative 4. So this is much closer, 2.127 versus 2.13. And so we just round this, and then it comes out to 2.13. So it's a better answer using the quadratic. All right, but that's not the only hydroxide producer here. We also have step 2. Now, step 2 depends on what's bigger. There are 2 more hydroxide contributors. So when we go to step 2, the question we ask is this. Should we do KB2 or KW? KW is 10 to the minus 14. What is KB2? So KB2 for carbonate is equal to KB for bicarbonate, which is going to equal KW divided by Ka for what acid? For carbonic acid, which is 1.0 times 10 to the minus 14 on the top divided by Ka for carbonic acid on the bottom. Ka for carbonic acid is 4.4 times 10 to the minus 7. We'll put 4.4 times 10 to the minus 7, bottom. And then calculate that. 1 times 10 to the negative 14 divided by 4.4 times 10 to the negative 7. Gives me a KB2 of 2.27. 27 times 10 to the minus 8, 10 to the minus 8. So Kw is 1.0 times 10 to the minus 14. Kb2 is 2.2727 times 10 to the minus 8, so we do Kb2 next. If Kw were bigger, we do Kw next. Sometimes that happens. Yeah. And so doing Kb2 next, we are going to have bicarbonate hydrolyzing water. Bicarbonate can hydrolyze as an acid or it can hydrolyze as a base. In this case, we need a bicarbonate to hydrolyze as a base. Which is going to form carbonic acid plus hydroxide. And so this is the Kb, which is 2.2727 times 10 to the minus 8. Okay, then we solve this stepwise with a nice table, and then see, does this step 2 perturb step 1? If it does, we got to go simultaneous. If it doesn't, then we just leave it as the second step and then move on to step 3. All right, I'm going to stop here. So we'll take a break for like 10 or 15, and then we'll start again with the lab after we come back. We're going to break up this lab into 2 days. So I'll talk about it when we come back from break.